All right, so this is day 2 of our introduction to derivatives. Now we're going to look at things graphically. So we talked about yesterday how the derivative of a function f of x is the slope of the tangent line at C. So now we want to do just some investigations comparing slopes, basically. So use the graph to estimate f prime of 1, f prime of 3. So f prime of 1 is the tangent slope at 1. F prime at 3 is the tangent slope at 3. F prime of 5 is the tangent slope at 5. So let's just estimate what we think those are. So F prime of 1, I'm going to say, what do you think that is? Like 2 maybe? And F prime of 3 looks to be the relative maximum. So I'm going to call that one 0. F prime of 5 is negative for sure. Do we think it's negative 2? Maybe it's a little steeper, negative 2.5. These are just estimates again. And f prime of 6, that looks to be about 0 to me as well. I guess I could have put equals. I thought we were going to do something with them. And then what about these? F of 1 and f of 3. So watch the notation here. This is just what's the function value. So f of 1 is equal to 3. And f of 3 is equal to 6. Among the numbers, arrange the numbers in increasing order. So we're not talking about steepness. These are all slopes. We're not talking about steepness. We're talking about numerical order. So f prime of negative 3, that's like here. I'm just going to sketch these in. F prime of 0 here. F prime of 2 is here. F prime of 4 here. Increasing order, that means low to high. So we have negative slopes, maybe a 0 slope, and a positive slope. So the highest one is this positive slope. So f prime of negative 3 is definitely the largest. And then the smallest is the steepest negative, because negative 4, for example, is less than negative 1. So f prime of 4 is the smallest. And then I'm going to go with f prime of 0, because f prime of 2, if it's not 0, it's close to 0. So the closer you are to 0 with negative numbers, the higher that number is. Number 3, given that the tangent line to the graph of y equals f of x at the point 2, 5 has this equation, find f prime of 2. So this is a tangent line equation. F prime of 2 is equal to the slope. It's just equal to 3. Given that the tangent line to y equals f of x at the point negative 1, 3 passes through the point 0, 4, find f prime of negative 1. So again, we're talking about the tangent line. F prime is the slope of the tangent line at negative 1. And so all we have to do is find the slope between these 2 points. Because f prime of negative 1, the slope of the tangent line, will be the slope between any 2 points on that line. So 3 minus 4 over negative 1 minus 0. Negative 1 over negative 1 is positive 1. So f prime of negative 1 is equal to 1. Let's see. Sketch the graph of a function f for which f of 0 equals 1. So f of 0 equals 1. Plot that if it's not already on your graph. F prime of 0 equals 0. So I like to dot in just a little horizontal tangent to remind myself that I should have a relative max or min right there, maybe. F prime of x is greater than 0. So if the slope is positive, that means that f is increasing. This is going to be a huge concept for like half of our year. Just if you're told the derivative of a thing is positive, it means the thing itself is increasing. That's if f is less than 0. So that's to the left of 0. So f needs to be increasing to the left of 0. And then f prime is less than 0. So if the slope is negative, then the graph of f must be decreasing to make that negative slope. And that's to the right of 0, something like this. So it probably looks like a little bit of a parabola that opens down. Sketch the graph of a function for which f of 0 equals 0. So plot that if you don't have it on there. F prime of 0 equals 0. Kind of dot that in. F prime of x is greater than 0, so f is increasing. to the left, and f is increasing to the right. So we have to go increasing, 0, increasing. So that's kind of like a little that's kind of like a little cubic curve or something, right? Because you want your slopes to be getting more shallow to 0 right here, and then they get positive again, more positive. Given that f of 3 equals -1 and f prime of 3 equals 5, find an equation for the tangent line. So to write an equation for a line, you need a point and a slope. And they've given us both of those things, so this is super easy. Y minus -1 equals slope times x minus x1. Given that f of -2 equals 3 and f of -2 equals -4, find the equation for the tangent line to the graph of y equals f of x at the point where x equals -2. So same thing, we have a point, we have a slope, so we can easily write point-slope form of that equation. All right, now this can get kind of challenging. It depends on how kind of visual you are. So I hopefully have some tricks to help you out with this. We want to match the graphs of the functions shown in lowercase a through f. So these are the f of x graphs. We want to match them with their f prime graphs, which are capital A through f. So start on the linear ones. Those are the easiest ones to identify. So we are looking for a derivative graph that has some constant positive number and then switches to 0. So a positive horizontal segment and then 0, that's right here. So D goes with A. And then this is our only other linear one. So we have like a negative, then a positive slope, then a negative, then a positive. So that's got to be F. That's the only other one with horizontal lines. So if your graph for f of x is linear or has linear pieces, then your derivative slope will be horizontal segments that correspond to those slopes because they're constant slopes. If your f of x is curved, you're going to have curve to your derivative graph as well. So let's take a look at C. What about the slopes on C? So there's a 0 right here. So we're looking for a derivative graph that goes through 0, 0. So maybe B or maybe E. And it starts out kind of towards 0, and then it gets positive, more positive, less positive to get back to 0. And then it gets a bit negative, more negative, less negative, back to 0. So that's looking like B to me. Close to 0, positive, back through 0, 0, dips into the negatives for a while, comes back to 0. So that's lowercase c, goes with uppercase B. If your f of x has an unbounded discontinuity, then your derivative function will have the same thing. So the only one that has that is c, but let's still look at this. So we're starting off kind of close to 0, kind of flat, and then negative, negative, really negative, really negative, and then really negative, less negative, 0. So oh, wait, I just said, oh, not negative. Sorry, these are positive. Positive, positive, super positive, 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 positive. I was going to say, I don't see a graph like that. That's this one, right? It's close to 0, but negative, and then it gets super negative down here. And then it starts off really positive slopes or really positive f primes and then getting closer to 0. So capital C goes with lowercase d. Let's take a look at graph E. This graph is always increasing. So its f prime will be always positive. The only option I see for that is A. Again, let's kind of go through it. So you're starting close to 0 and getting positive, positive. The most positive it will be is at that change in concavity. And then positive, positive, back to 0. So yeah, that's A, goes with lowercase e. That means F has to go with E. So, okay, but let's again discuss. So this one has endpoints. And the slope is 0 right here, which matches this. But then, like on either side, these are positive slopes that get more positive as you go down. And these are negative slopes that get more negative as you go to the right. So as you hit that endpoint, as you approach it, the slopes are just going to keep getting steeper and steeper and steeper. All right, find a function f such that f prime equals 1 for all x and give an informal argument to justify your answer. So the slope has to be 1 for all x. I would just do a linear function. So f of x could just equal x. My informal argument is because this function has a constant slope of 1. All right, now we're going to do what we just did in number 9, but we have to draw the graphs for the derivatives. So you have f of x. We have to draw f prime, also known as the slope graph or the derivative graph. Kind of do it the same way I was doing to identify. Start by plotting zeros if you can. So, and let's start with an easy one. Let's skip this first one, go to this one. This has a slope of 0 no matter what. So I have a horizontal line going through 0. Let's find another linear one. This has a negative slope of some sort, a sharp turn. So no slope there, or not differentiable, I should say. Actually, let me use that language. Not differentiable. So we should have a discontinuity in our derivative graph, and then really negative here. So some sort of constant negative slope, a hole at 0, and then it drops down to a bit more of a negative slope and continues on. Let's do the last little linear one. My pen is starting to give out, so let me try to fix this. 0 slope to 0 slope, there's a discontinuity here, so not differentiable at this point. So a hole at 0, but otherwise the slope is 0 everywhere else. All right, so what about these curved ones? So just start at the beginning, so kind of a 0 slope, kind of level, and then getting more and more positive, and it just kind of grows without bound. So 0 to growing without bound. Remember, where you have an unbounded region in f of x, you'll have an unbounded region in f prime. Now you have to trace this one going down, so the first slope here closest to 0 is really negative, and then it tapers off until you get back to 0. So really negative, and then getting back to 0. On this one, I see 3 little relative extrema, which means that at those corresponding points, your derivative graph should equal 0. And then we're really negative until we approach 0. So really negative until we approach the first 0. Then positive until we get to the next one. So dip up into the positives, back to 0. Then negative again, into the negatives, and then positive. We can't be picky about how far you go up, positive or negative, because we don't really have numbers for these. Last one. This function is always increasing, so your derivative graph should always be positive. The steepest that it will ever be is right here in the middle. But otherwise, it's like kind of close to 0 and getting more and more positive, and then kind of tapering off again to get back to 0. So there should just be a peak in the middle where you have your steepest or highest number slope. Estimate f prime of 4 by finding f of 4 and f of 4.01, where f of x equals x squared minus 3x. So f prime of 4, we're saying it's about equal to f of 4.01 minus f of 4. That should say f, not 4, over 4.01 minus 4. So, I don't know what this squared is going to be. Let's see. Get Desmos out here. Squaring in decimals, and it's May when I'm doing this video, and I just don't want to deal with that. So, plus, good chance to check out Desmos again. So, f of x is equal to x squared minus 3x. And I would like to calculate f of 4.01 minus f of 4 over, I could do this math. All right, so this is 5.01 as our estimate for the derivative or the tangent slope. So we're saying, okay, f prime of 4, it's about equal to 5.01. I bet the exact answer is 5. use the definition of a derivative and then use this formula to find f prime of 4. No, I'm going to use the alternate definition because it's silly. If you're trying to evaluate a derivative somewhere, you don't need the derivative equation. You can use that alternate form, which says, here's the alternate form. If you want to evaluate f prime of c, so this is not this wouldn't work if it just said find f prime of x. I'd have to do the long way with the difference quotient. But this is if you're supposed to ultimately plug a number into it, evaluate. It's equal to the limit as x approaches c of f of x minus f of c over x minus c. This is something to memorize. So ours is f prime of 4. It's the limit as x approaches 4 of f of x, so x squared minus 3x, minus f of 4. So what do I get when I plug 4 into this? 16 minus 12 is 4 over x minus 4. Direct substitution doesn't work here. You get 0 over 0. But if you work on this a little bit, you can factor. And the x minus 4s cancel. And 4 plus 1 is 5. All right, so that means that, like I predicted here, f prime of 4 is exactly equal to 5. Our approximation was pretty good, but this is how we find the exact answer. All right, arrange the following values from smallest to largest. So all of these are going to be positive numbers because g of x is increasing. So the first one represents the slope between g of 1 and g of 2. The next one represents the slope between g of 2 and g of 3. And then g prime of 2 would be in between those, right? Because it's the tangent slope in between those. G prime of 3, and then g prime of 1. So I think g prime of 1 is the lowest. And then we do the average rate of change between 1 and 2. And then we do the derivative at 2, the tangent slope at 2. And then we do the secant slope between 2 and 3. And then we do the tangent slope at 3. And I think that was all of our numbers. Draw a graph of f of x which satisfies the following conditions. So do the easy part first. Plot f of negative 2, which is equal to 4. There will be a horizontal tangent there. F prime is less than 0, so f is decreasing to the left of negative 2. And again, f prime is less than 0, so f is decreasing to the right of negative 2. So the horizontal tangent is because we have something decreasing, you got to level out, and then decreasing again. Something like that. Write the equation of the tangent line to the function y equals f of x when x equals negative 5 if we have this point and this slope. That's easy. Y minus 4 equals negative 1/2 x minus negative 5. Number 16, draw the graphs of the derivatives of the following functions. So let's just go in order here. So here's a 0 and here's a 0. So let's try to translate that to their correct location. Positive, positive, positive. So positives until we get down here. Negative, 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 negative. So dip into the negatives. Positive, positive, positive. On B, f of x is not differentiable at the sharp turn. Otherwise, it has a positive slope and a negative slope. They look to be about the same, like steepness. So at negative 3, there's a discontinuity, but we start out with a positive slope to the left of that. And then to the right of that, we have, I'm going to go the same distance, negative slope going to the right. We have 0, 0, 0, 0. So that's 2 zeros on the left, 2 zeros on the right. Starts out positive, then goes negative, positive, negative, positive. So starts out positive, goes negative, positive, negative, positive. This one, there's a vertical tangent where this ends, because if your negative slopes are you're starting 0, and then you're getting more and more negative, I could keep getting closer and closer to whatever that point is. I could just add another decimal place and scoot closer to it, and I'll get an even steeper slope. So there is a vertical tangent there. So whatever that is, I'm drawing in a vertical tangent. And then these start close to 0, but they get more and more negative as you get closer to that end point. There's a discontinuity, an unbounded discontinuity at 0, so there will also be an unbounded discontinuity on f prime. Starting out close to 0 and getting really positive, and then starting out really negative and getting closer to 0. So close to 0, positive, really negative, close to 0. There's a 0 over here. Start out close to 0, positive, 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 negative, 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 back close to 0. So start out close to 0, and we're getting somewhere in here, we get like pretty positive until we change back. So it's like, I don't know exactly where that happens. And then we get negative, but we dip back to 0 as well. Okay, final one. F of 3 equals 1. Horizontal tangent. F prime is less than 0, so F is decreasing to the left of 3. F prime is greater than 0, so F is increasing to the right of 3. Sometimes I do this, decreasing then just to remind myself like what that's going to look like before I draw stuff. So something like that. All right, this takes some practice, so make sure that you do the homework that goes with this assignment. And please come and see me if you just want practice in office hours. These are easy problems to kind of make more practice of.